So finally, we can talk about the entropy change for a reversible process. So if we have a system that is completely reversible and the system moves from one state to another, you notice the TS diagram there on the page, and we go from, say, 0.3 to 0.7 kilojoules per Kelvin for the system. Remember, entropy is a property of the system. Then we can calculate the change in entropy of the system as simply the difference in the entropies at those two states, so 0.4 kilojoules per Kelvin. And if we do this, really what we're doing is integrating this equation that is the definition of entropy, but it's a pretty simple thing. And so changes in entropy can be calculated simply based on the value of the entropy in the two states. Now, just like energy, we have to have some reference point, okay? If you notice, think about enthalpy. Look at the steam tables in your book. And the enthalpy must have some zero state. We have to decide what that zero state is. Just like with this pencil, we have to decide what we're going to call zero energy, right? At one moment I had the table as the zero energy point. At another time I had the floor as the zero energy point. I changed the reference on you is all I really did. We have to have a consistent reference if we're going to talk intelligently about this and use it effectively. So if you notice in your steam tables, there are columns for the entropy of the steam, or R134A, whatever you happen to be looking at, but that entropy does have a reference value where the entropy is simply defined to be zero. Now there's another way of looking at it which I'll show you in just a moment, but what's important here is that this thing, dq over t, is a property that we're going to consider to be entropy. Now this seems kind of theoretical, right? I mean, we did all this math and logic reasoning and okay, whatever, but what good is it? I mean, after all, internally reversible and reversible processes are theoretical things. So it's kind of like a mirage, right? It's like we're in the desert and we see an oasis, but it's really far off and it's probably fake anyway, right? What good is it? Well, actually, we can do something really useful with this, believe it or not, because I know that this is a theoretical process we could never accomplish, right? This move from state 1 to state 2 for a completely reversible process, never going to happen. So what good is it? Well, actually what it'll do is it'll help us get the mathematical statement of the second law that we're really interested in, not just some integral equation. So finally, we're going to get the entropy change for a real process. Now remember the Clausius inequality that says that this cyclic integral dq over t is less than or equal to 0. Okay, so let's consider a really simple cycle, a cycle that consists of a reversible or irreversible, preferably a real, in other words, irreversible process from state 1 to state 2, and an internally reversible, at least, process from state 2 to state 1. You can think of that as a completely reversible process, that's fine. Now, the cyclic integral, the Clausius inequality, says that if we start at state 1, go via the real process to state 2, and then back to state 1, add up dq over t along that the entirety of those two processes, we'll get a sum less than or equal to 0. That's what the Clausius inequality says, and this makes sense because one of these is a real process. So in fact, we would get something strictly less than 0. But we can break up the cyclic integral into an integral that's two parts. One integral over the process from state 1 to state 2, and then an integral over the process from state 2 to state 1. And so you see that these two integrals, these two terms, are two separate pieces, right? The first piece, the integral from state 1 to state 2, represents the real process, and then integral from 2 to 1 represents the reversible process. And we've got the appropriate subscripts there as well. So all we've done really is broken up the cyclic integral into two parts. Now be careful, on page 241 there is a mistake in your book, and if you're trying to follow along and really dig into this and understand it, this may throw you for a loop because they substituted the order incorrectly. I've got it right in the slides, but they had 1 to 2 for both of these. If they were going to do 1 to 2 for the second term, they should have put a minus sign in front of it. I think the easiest way to understand it is just you should flip those two limits, because we're integrating from state 2 to state 1 in the second term, not the other way around. Okay, so make sure you make a note of that in your book on page 241. It's the second equation. I don't believe it has an equation number as I recall. But all they're really doing is breaking up the cyclic integral into two parts. So once you've made that change, notice that the second term, right, the integral from state 2 to state 1, that we've already seen as a property of the system, and so can simply be represented as the amount of entropy in state 2 minus the amount of entropy in state 1 if we're going from state 1 to state 2. I think this is where the book got it backwards, okay? Because the order you see here for this integral is opposite what I have in the equation before, but there's a reason for that. We can then rearrange this and substitute S2 for S1, or S2 minus S1 in for the integral, except we need a negative sign. So it'll be S1 minus S2. So you see that internally reversible subscript labeled integral. We've eliminated that in favor of S1 less S2. Okay, so the first integral represents the real process. The second integral we've replaced by S1 minus S2. And so now we can move S1 minus S2 to the other side. But of course, we flip the sign again, and now it becomes S2 minus S1 is greater than or equal to that integral for the real process. Okay. Now, I don't know about you, but I've never liked inequalities. I mean, in programming, they're okay. They allow you to do comparisons. In math, most of the time, they don't do much good, right? I don't know an algebra of inequalities. To solve equations, you really need equalities. And so, to effect that, what we could do is simply add something to the left-hand side. If the right-hand side is bigger than the left-hand side, which it would be as long as the left-hand side is a real process that's irreversible, then we just need to add a little bit to the left-hand side, and voila, we've got an equality. So let me flip the two sides around so we can write it in a form that's really useful. S2 minus S1, in other words, the actual entropy change of a real process between the two states, will be the integral of dq over t plus a little bit. And that little bit we'll call Sgen. It's generated entropy. So in other words, for real processes, the entropy change that we get is the sum of all the little dq over t's that happen in going from state 1 to state 2 plus some more. It's kind of like saying my bank account balance changes from $100 to $200 because I added $1 every day for 50 days, so that's $50. Plus, somehow $50 just came in. The $50 is the Sgen. Maybe I should have made a better analogy. Maybe dq over t would be $75, right? $1 a day for 75 days, and then Sgen is $25 that somehow just appeared, right? If you do that in the real world, that's called stealing, right? You'll probably go to jail for that. But in our case here, this is the way things actually work. And you might look at this and say, oh, you mean we're getting something for free? Yes, we are. In fact, Sgen, the generated entropy, is something that simply is generated. And it's a measure of essentially how energy is spreading out is what it is. But it's something we get for free that we don't want. So we finally found something we can get for free. And oh, by the way, it's something that degrades the performance of all our engineering systems. So this is something we don't want, but it's something we must learn about so that we can contend with it and hopefully still optimize our engineering systems. So what this really means is that even if a system is completely isolated, its entropy change can be greater than 0, because entropy can be generated just because that's the nature of the universe. That's just the way things work. So irreversible processes generate entropy. Reversible ones generate none, but it's impossible to have a net destruction of entropy. If entropy decreases in one area of the universe, it must increase somewhere else. And what that really means is that when you take gasoline, which is fairly ordered and put in your car, and you burn it to push your car down the road, entropy is generated. The energy that was concentrated in that gasoline in the form of chemical energy has now been changed into thermal energy, which will naturally simply spread out. And you toss it out your tailpipe as hot exhaust gases, right? And it all naturally just dissipates and spreads out. That's a generation of entropy. Okay, and that's what makes processes go forward, because processes will only occur when entropy is generated. Entropy is not a conserved thing. It is created from nothing. And unfortunately, engineering systems are degraded by irreversibilities, and Sgen is actually a really nice measure of the magnitude of irreversibility. So the more entropy that is generated, the lower the performance of engineering systems typically.